Okay, so here's the problem. We know that we benefit from an increasingly large network of observations of the sea ice cover, and still these observations are very variable, but they're only a small part of the full picture. So they are very valuable, but they are not sufficient to characterize properly the whole sea ice state, the whole ocean state. And the problem is that we know that a significant part of the memory of the system that will be used for advancing predictions is probably residing in this information on the full sea ice state. And to make the picture even more complicated, we know that the few observations that we have a very large uncertainty. Well, they have uncertainty. And so clearly at this stage we need another source of information to complete the picture. And this source of information comes from the models. The models have the advantage to explicitly simulate all these variables, but they are models, so only approximations of the reality. And how to optimally combine these two sources of information, so observations on the one hand, models on the other hand, has a name, and it's called data simulation. And data simulation is a really fascinating subject on which I've been working for now 2 years. It's fascinating because it has a very strong mathematical background and basis, as Frank showed, but also because it's really a tool that is making the connection between two communities, the communities of people that make observations and community of modelers. And I think it might be a very promising tool for advancing predictions in the Arctic. So I want to go in 2 steps and first look at a very simple sea ice model to really understand what are the central ideas of data simulation, and then move to a more operational model, large-scale model, to see how data simulation can help improve the prediction in the Arctic. When I'm saying I'm using a very simple model, it's a very simple model. This is just one flow model with no ice concentration. It has only 2 variables, ice thickness and surface temperature of the ice, so 2 variables. And basically it's responding to changes in fluxes from the atmosphere. Now we can suppose that we have observations of sea ice thickness, and we want to assimilate sea ice thickness in this 2 variable model. And this is the result. No. This is the result. So we have time here, we have sea ice thickness here. The blue curve is the reference model without any data assimilation. The red curve is the true thickness that we cannot even observe because the observations have uncertainties. And what data assimilation will do is just update thickness in a way that it's consistent, so that in the end you will have the green curve, which is what you call your reanalysis, and which is a kind of interpolation of the observation, and which is consistent with the true thickness. But that's not a big deal. This is just what we could call primary nudging. And the real question that we should ask ourselves is what happens with the other variable, which was surface temperature of the ice in our model. So I'm going to focus on this box here and look at what's happening in my ensemble. So I have here 100 realization of my model. I perturb the flux in the atmosphere for each of the member. But even if I apply some perturbation in the ensemble, I have some structure in the model. I have relationships between my 2 variables, sea ice thickness and surface temperature. And when you do simple nudging, if you have observation somewhere of sea ice thickness, when you do simple nudging, what you do is just you bring the gray dots closer to observations, but you forget one important thing. You don't update the temperature of the ice at the surface. And what you do if you do simple nudging is that you just break the relationship in your model between the 2 state variables. If you break these relationships, then it may have very undesirable consequences for predictability, because you might bring your system into an unbalanced state and you may just lose predictability after the first step of initialization. So what's the way out? Well, if you want to go forward, you have to take into account that you have some structure in your model and update each of the member to keep every dot inside this envelope of of model forecast. So this is very much the key of data assimilation, multivariate data assimilation, is to take into account the structure of your model when you assimilate one variable to update the other. So really, this is the first message that we cannot do data assimilation on one variable only. We have to consider the full CI state. Now, if we move to a more comprehensive CI model, the questions are essentially the same, which is the good news. The first question is, how do we make the interfacing between the grid cell information that is given in the observation and the subgrid scale information in the grid cell information from observation and the subgrid scale information from the model? How do we update the variables that are not observed? The second point is, how do we make sure that we pour the necessary information to give the memory, the necessary memory in the system, and to improve the prediction? And the third question is, how do we make sure that we keep the system at all times in good dynamical balance? And we are doing this with an ocean sea ice model, which is NEMO and LIM3, which is followed by atmospheric reanalysis. And the answer to this question is very simple. It's the same for the the simple sea ice model. You have to account for the fact that your your model has some internal structure. You could think that this is the observed ice concentration, and here it could be ice thickness in the first ice category. It could be the SST, it could be SSS, could be snow depth, whatever. As long as there is a relationship between the two, you have to account for the fact that you will update these non-observed variables. But the point is that the correlations are not obvious in large-scale models. Yesterday we had a nice image from Stefan about what he called an old paper of 2003. It's maybe old, but it's still valid and very interesting. And I have here shown similar results with our model. The maps are showing the correlation between concentration that we observe and thickness in our ensemble. So we have 25 members. Each of the members is perturbed by changing the atmospheric forcing. And in winter, it's pretty much what we all think here. With higher concentration, we have thicker ice, which is just a thermodynamic argument. But in summer, it can happen that we have these negative correlations. Because in summer, my interpretation is that we are at temperatures of the air that are above freezing point, and that the winds play a bigger role in shaping the ice cover. If we have anomalously large winds, then the ice will pile up easier and will increase ice concentration, increase open water, decrease concentration, but increase ice thickness. So it's not surprising that we have this anti-correlation in summer. But in any case, you see that the way that variables covary in your ensemble is not obvious at all. Now, is it relevant for prediction? Well, I think it is. This is a plot that we saw a version of that plot yesterday. It's showing the error in September forecast in the Arctic for ice concentration for several years. The red curve is the control run, so just forecasts without any initialization. And the blue curve is the error for initialized run. So when we assimilate concentration and let the model evolve for 6 months from March to September. And you can see that systematically we have an improvement. Just from the information of ice concentration, we have an improvement in the simulation of September, just because of this mechanism of ice concentration, ice thickness. So I think this is promising. So yeah, if we account for the fact that concentration and thickness are related, but that is not obvious, probably we can move forward and advance Arctic sea ice predictions. So I want you to take home 3 messages. Yeah, the first one is that you cannot do data assimilation just on one variable. That's the only thing that you will do is probably to bring your model out of balance, which is even worse than doing nothing, I think. The second point is that it's not easy to update not observed fields, and you have to make it in a very formal way. And the third point is that it's necessary and worthwhile to do such data assimilation. I think if we want to improve the predictions using large-scale models. Thank you.
Thanks. We have time for 4 minutes of questions. So would anyone like to ask a question? And maybe we'll get a microphone runner in hand. And it can be either to Francois or Franck.
I wonder, when you compare the errors for initialized versus uninitialized, are the uninitialized run, don't they have any SST even information? I wonder, do they have any information about sea ice that's not concentration? And do you really think that the currently assimilating concentration will improve this data assimilation?
So this non-initialized run, I think you're right, is not really not initialized because it's forced by atmosphere, and the atmosphere itself is a reanalysis product, meaning that it's been run with prescribed ice concentration during the reanalysis stage. So we indirectly use twice the information of, we use the information of ice concentration here indirectly, and here we use it twice because we assimilate concentration and we run with a prescribed atmosphere, which is based on itself on the ice concentration products. So it's just to show this is just showing the pure sensitivity of the seasonal hindcast to initial conditions. The only difference between the two is the change in initial conditions in March.
Yeah, I was just going to ask, obviously you show the link between ice concentration and ice thickness in the model. Obviously you can either take the mean ice thickness where there is ice within a grid cell, or you can take the volume of ice per unit area in your grid cell. And so whether that would change the conclusions from the discussion you showed earlier.
So the correlation that I showed are between concentration and in situ thickness, so not including open water.
Yeah.
And your question is, would I have the same correlation if I would include concentration, open water?
If you go to the previous slide,
yep.
So that was, yeah. Okay, so this was all from.
But it was a generic, just to say how to update variables that we do not observe compared to the one that we observe.
Yeah. Okay. Yeah.
We'll take one more, and
A slightly more general question: is anyone thinking about assimilating sea ice age or something like that, where we have some observations? Cecilia's thinking about it, and it depends if your model's got ice age output, presumably.
It does. It does have ice age, although I think it's a tracer in the model. The problem I see directly is that definitions are not the same in observation and in models. In models it's a tracer. In observation it's I guess I'm not a big specialist on that, but I think you trace ice and you deduce for how many years or something like that it's been there. And so I think the definitions are different. And if you maybe I said something wrong, but for the observations, but there's a risk that you will assimilate something that is not exactly the same in the models and in the observations. It's a bit like if you were to simulate thickness against weighted open water weighted thickness or something like that. So.
More categories.
Okay, thank you very much. That was very informative, and